All right, guys, so here's notes 3. These are today's notes. Hopefully everyone's having a good time, and hopefully everyone's happy. We're going to go ahead and get started. This is limits connecting asymptotic behavior plus properties and cool stuff. I didn't put a hashtag. Maybe next time I'll put a really cool hashtag. So I know I put yesterday in here. It's actually the day before yesterday. No big deal. We had this graph, and here we have this graph again. Why do we have the same graph? Well, because I didn't want to create a new one. So there's my old graph. And then we said the location of the hole was -376. And we already expanded it, and we did numerical analysis on that, on what's happening. I don't remember if we did what's happening as we approach -3 from the left and -3 from the right. Obviously, as I approach -3 from the left and -3 from the right, I'm approaching some y value, and that y value can be found by expanding that guy. But someone do me a favor and go to decimals.com. Maybe, Mazuka, is it okay with you if in a little bit we have you share your screen and show what's happening as we approach 3 from the left? Is that cool?
Yeah.
So hit up decimals.com. I'm going to stop sharing, and I'm going to allow you to share.
I have it.
Okay.
So let's hope I don't mess up like yesterday.
You're not going to mess up. You're a pro now.
Over
Perfect.
x squared minus 9. Okay, table.
Perfect.
Yay. Okay. So the first one is -3.75. The next one is -3.1. Next one is -3.01, and the last one is -3.001.
And then just for kicks, put -3. And you can see it's undefined. So remember those numbers, guys? Write those numbers down on your table and then hook me up with them in a little bit when I go to my screen. All right, Mazuka, stay on decimals.com because in a little bit we're going to have you do it again. What was it at -3.75?
Okay, 1.2592.
And then a -3.1?
1.1803.
1.1803 and a -3.01?
1.168. And if you round up, it's 1.1681.
And then this one was probably 1.1668.
Yes.
Okay. Now, if we do the same thing, so obviously it says if I'm approaching 3 from the left, I'm approaching some number. And the number that it looks like it's approaching, look, 1.18, 1.16, 1.166. So it's 1.166666667. And if you're wondering what that is in fraction, that is, looks like it's 7/6. So let's see if we're approaching the same thing from the right. And I think it is. It's going to be numbers slightly smaller because it's more negative than 1.16. So let's go ahead and take care of those. You want to take care of those, Mazuka?
Sure, let me share again.
Take out those numbers and put the other numbers in. You can also see the graph, what's happening. The points are converging. Perfect. All right, write down those numbers, guys, and then hook me up with them in a little bit. All right, what were the numbers at -2.75?
Okay, 1.1304.
1 and -2.9?
1.1525.
And then this -2.99 is probably 1.5. 9.
Actually, it's 1.16523.
1.6523, and then this one's 1.166.
Oh, I'm sorry. It's the negative 2.99 is 1.1653.
1653. And
And
then
then
this one's 1.
1665.
And you can see again, guys. All right, thank you, Mazuka. I appreciate you. You can see again, guys, that it's approaching the number 1.166666, which is the same thing as 76. So because it's approaching the same thing on the left as it is on the right, you can say it's just approaching 76. Now, of course, did we have to do a table for this? No, you could have just done what we did last time. F of x equals, I'm just writing the equation down, guys. 2x squared plus 5x minus 3 over x squared minus 9. Okay, so if I have that function, I'm going to go ahead and I'm going to say limit as x approaches -3 of this function f of x. If I do direct substitution, guys, you get 0 over 0. Remember, if you get 0 over 0, it definitely has a limit. You don't know L'Hopital's rules yet. So because you don't know L'Hopital's rule, you're going to have to do it algebraically. So in the top, let's see. The only way, well, I shouldn't be writing that yet. So I'm just going to factor it over here, guys. So if I factor this out in the top, the only way to get a 2x squared is 2x times x. And the only way to get a 3 is 1 times 3. But I needed to add up to a 5x. So the 3 goes here and the 1 goes there. 2x times 3 is 6x. So that has to be the positive one. And then 1 times x is 1x. So that has to be the negative one. And in the bottom, that's just the difference of squares. X plus 3, x minus 3. Now those two cancel out. See? So if I plug in direct substitution now, because now you have 2x minus 1 over x minus 3. If I do direct substitution, 2 times -3 is -6, minus 1 is -7. Relax. You're going to get another negative number in the bottom, which is going to cancel it to make it positive. And then -3 minus 3 is -6. Negative divided by a negative is a positive. So there it is. And yes, maybe you're saying, like, man, Chavez, you just made me waste 5 minutes doing this table. What's the whole point of doing a table when I could have done it algebraically? You're right. I just want to show you that you can get this answer also with a table. Like you can see that it's approaching, it's converging at 1.166666, which is just 76, guys. Sometimes a table helps. Sometimes algebraically is the best route to go. All right, so now we're going to do something. We're going to be approaching negative infinity. Let's get someone else besides Mazuka. So how about Ms. Godinez? Would it be cool if we shared your screen?
Yeah.
All right, so let's get ourselves prepared. Type in this function into desmos.com. If I don't know if you already have it in there or not, but if you don't, let's start typing it in. And we're going to be plugging in these numbers. And yes, I know that we can already tell what's happening, guys. Look what's happening. So we already know what that number is going to be, but let's see if Desmos will tell us. So let me go ahead and stop sharing here. There you go. Do you have the numbers with you or no? Okay, you got it. There they are, guys. Write down those numbers. All right, I'm going to force this. Hook me up with those numbers, Godinez. At 50, when x was -50, what'd you get for f of x?
1.9056.
What about a negative 100?
1.9514.
A negative 500?
1.9900.
And a negative 1,000?
1.9950.
1.9950. Okay. So you can see here, as x approaches negative infinity, it looks like it's converging. I bet you I would have gone to 1.999 if I would have put negative 10,000. It looks like it's converging at what number? Not everyone at the same time. It looks like it's converging at 2, guys. Yeah, try not to let me talk by myself, guys. I want to hear y'all's voices from time to time because, you know, just listening to my voice probably gets boring. So let's go ahead and do the same thing. All right, Godina, let's do it one more time, but this time for positive infinity. And I'm going to allow you to share your screen. So let me stop. Perfect. And you can already see that the numbers are above 2 because, you know, there's my horizontal asymptotes at 2, and you're getting closer and closer as x gets larger to the number 2. So write those numbers down, guys. I'm going to go ahead and do the force here, the force share. So sorry, don't get mad. Hook me up with those numbers, Godinas.
At 50, it's 2.1063.
At 100?
2.0515.
0515. At 500?
2.0100.
And at 1,000?
2.0050.
Again, limit as approaches infinity is 2. So we're already making an observation of what happens negative infinity, positive infinity. And maybe I think if I would have done correct notes, I would have probably talked about horizontal asymptote right here. We'll talk about that in a little bit when we start concluding. Let's see what happens as I approach 3 from the left-hand side. So let's get someone else. Ms. Dinan, would it be okay if we bother you on this function?
Yeah, I can.
All right, so if you haven't had a chance, go to Desmos and type that little guy in. And I'm gonna stop sharing in a little bit and then I'll put yours in. Stop sharing. Oh, what happened? Perfect.
Is it +9 or -9 in the denominator?
It was x squared minus 9. You have a negative 2 in the x. Do you see that? Right, yeah, right there. There you go. And then table.
Can someone tell me the numbers?
I think, can you guys help us out, guys? Was it 3.1?
2.75.
Okay. And then
9.
2.9. Was the next one 2.99?
Yeah.
And then the last one, is it 2.999?
Yep.
Okay. So there's, and then that was it, I believe. So there it is, guys. Put those numbers in there. And you know what, to make things faster, Dinan, we're just gonna continue. And then a little bit, we'll get the numbers and transfer them. All right, so let's put, all right. So now just erase the ones, those numbers, and let's type in, I'm assuming I put 3.25 if I put 2.75 the first time.
You put 3.75.
Oh, I did? Oh, man. Okay, 3.75. And then what did I put after that?
3.1.
3.1. Yeah, if I would have been better, I would have probably done the same spacing, but oh well. 3.75, 3.1, and then 3.01, I'm assuming. And then I'm assuming that then I did 3.001. And I think that's it. All right, write those numbers down, guys. All right, let's see. So can Ms. Godinez or Dinan, someone, it doesn't matter who, can you guys give me these numbers as I approach 3 from the left and then 3 from the right?
3 from the left starts with negative 18,
Mhm.
negative 48, negative 498, and then negative 4,998.
4,998. So this looks like negative infinity. And then the one on the right from 3.75,
8.6666,
okay?
52, 502, and 5,002.
All right. And then that one not converging to anything, so it just looks like it's getting bigger and bigger. So there it is, guys. I'm not converging to anything. It just gets larger and larger in the negative direction. And math is actually getting smaller because the more negative you are, the smaller you are. But it's so confusing to me to say that, guys. I just think the magnitude is very large in the negative direction, so I think it's easier for me and maybe even easier for you guys if we say it like that. But technically, this is like smaller in the math, and I've never liked that, but that's fine. You don't have to love everything. So yeah. So what can we conclude? I know you guys are probably saying, man, Chavez, you made this lesson really, really hard when all we have to do is look at this graph. I agree 100% with you guys. The whole point of this is that I want you guys to observe patterns. So here's what we can conclude. If x is approaching positive infinity and negative infinity, this is x, my x values. If you are converging on a y value, if it has a limit, that means you are converging on a horizontal asymptote. Let me say that again because I feel I said that all messed up. If x approaches positive infinity or negative infinity, if you have a limit, you will be converging on a horizontal asymptote. So what does it mean on math? It means this. So it says right here, observe asymptotic behavior. Observe asymptotic behavior. How are limits related to asymptotic behavior? If limit as x approaches infinity of some function equals a number. Usually they use the letter C or L. You know what? I'm not going to use C because we use C for vertical asymptote. So I'm just going to say equals some number. If x approaches infinity equals some number, then that number is a horizontal asymptote. So I'm going to say then that quote unquote number is horizontal asymptote. Not only for positive infinity, you can also check it for negative infinity. If limit as x approaches negative infinity of some function equals a number, then that number is a horizontal asymptote. Now there's going to be situations where you only have one horizontal asymptote on one direction, but you don't on the other. That happens several times, guys, especially when you have piecewise functions. You can have like negative x squared for x less than 0 and 5. So Travis, what are you saying? You're talking too fast. Okay, relax. I can have something like this. And then I can have like that. So this one, if I were to tell you what's the limit as x approaches negative infinity of this function, you would say it does not exist. Or you can also say positive infinity or positive infinity. Because positive infinity is a behavior. It just goes up forever. But if I were to tell you what's the limit as x approaches infinity, well, it's always 5 no matter what. Did that make sense, guys? You can say yes or you can say no.
Can you say the last part again?
Yes. If I were to write limit as x approaches infinity, oh, that's an 8. Infinity here of this function. Well, this function's always 5 no matter what. So that's kind of like a horizontal asymptote there because it's just 5. That's my end behavior. So see this one, this function, if I call this f of x, it's a piecewise. This one does not have a limit as you approach negative infinity. So you either say does not exist or infinity. That infinity just means it's a behavior. But a limit as x approaches infinity, if I approach positive infinity, the x values, I just approach 5. I know that's not a good job of horizontal asymptote because it's just a horizontal line all the time, but it's like a horizontal asymptote. Did all that make sense? What's up? Yes, ask.
So going back to like the last problem where it was as x approaches 3 from the right and from the left.
Oh, that's
So
different. But yeah, keep asking. Sorry.
I was just saying for the Delta math activity that we did, it said that whenever there's like really no pattern, that they just said that the limit did not exist rather than saying it was infinity.
Infinity is just a behavior. So you can say on the AP exam, they're not going to ever put both answer choices. Infinity is just a behavior. And actually, that's what we're just going to talk about next, about that one. So let's say I have this function. So look, I'm just going to draw something random. And I'm going to say this is my vertical asymptote. If I have something like this, and I'm going to call this C. So if I say limit as x approaches C from the left of this function, I'm approaching negative infinity. You can say negative infinity or does not exist. Limit as x approaches C from the right-hand side of this function, that's either negative infinity or does not exist. Which one's the better answer? They are both equivalent. Probably the better answer would probably be the behavior, the negative infinity. Now, let me talk about a different situation. What if you have this? So here it is. I'm doing a different situation again, guys. Here's C. I have this going like that, left, and this going like that, right. So this one in green, limit as x approaches C from the left-hand side of this function. From the left-hand side, I'm approaching negative infinity. Limit as x approaches C from the right-hand side of this function. From the right-hand side, let's see. I'm looking at the right-hand side here, guys. From the right-hand side, I'm approaching positive infinity. This one, if they were to ask you what is the limit as x approaches C of this function, the best answer on this one, you're not going to say negative infinity, you're not going to say positive infinity. For this one, the best answer is does not exist. Why? Because my behaviors are different. If I'm going from the left, I'm going to negative infinity. If I'm going from the right, if I'm approaching C from the right, I'm approaching positive infinity. My behaviors are different, so the best answer on that one is does not exist. The one in the blue, if they were to say limit as x approaches C without a plus or minus sign on the upper right-hand corner, you can either say negative infinity, because the behavior of both sides is approaching negative infinity, or you can say does not exist. The best answer, in my opinion, is the behavior one, but negative infinity, you're not converging to anything. So by definition, you don't exist because you're not converging to a number. Did that make sense? I'm assuming that was Tiff that was talking because I can't tell from
Yes,
name.
that makes a lot of sense. Thank you.
Okay. On the AP exam, guys, they will never, 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 and also myself, I'm never gonna, if it's multiple choice, they will never include both answer choices, like negative infinity or does not exist, because that's dumb. And I'll show you a few response questions where we had to grade these like a few years ago. The free response questions, the answer choice is gonna say either infinity or does not exist, and both would give you the correct point for that year. I think it was in 2016 where they had a limit problem, a free response, where the answer was positive infinity, and the students could say either positive infinity or does not exist, because the infinity is a behavior. It's not a number. It's huge. And by the way, I don't want to go off on a tangent. Go off on a tangent, but like it's hard to comprehend what infinity is because infinity is infinity. But yeah. So having said that, so here we go. I'm gonna start writing. What color do I want to write? I'm gonna write it in blue. No. Okay, what's up?
Sorry. I understand this, but I had another question about the delta math. Sometimes they would, like the y values, they would like go up and down and it wouldn't show a pattern, and that's when they would say it does not exist. What does that mean?
Oh, you mean like up and down? What do you mean? I guess I'd have to look at, because
just
I'm
like-
seeing this. When you say up and down, I'm like, okay.
Oh, well, like, yeah, I guess that's what it was. Okay.
Well,
never mind.
maybe sometimes there's an oscillation. Like if they tell you, well, okay, maybe it goes something like this. Sometimes there's something called like it isolates up and down, up and down, up and down, but then it gets bigger and bigger and bigger. So let's say if I approach 0, bigger and bigger and bigger, 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 boom. Like you can't tell. Like see, look at that graph. It's all nasty. Can you tell what the limit is as x approaches 0?
No.
No. So that one does not exist.
Okay.
And I think I don't remember the official name, does not exist because of isolation, oscillation. There's an official math name. I'll get it for you. and it's when something goes up and down, like huge, like with big magnitudes. And as you approach a specific number, it's going so fast up and down that you cannot tell anymore what it's approaching. Did I answer
Okay.
your question there, Godinez?
Yeah.
Okay, so here we go, guys. So how do I know when I have a vertical asymptote? C's a number. Oh, there's a little ant in my little table here, sorry. C's a number. So limit as x approaches C from one direction. If it says infinity or negative infinity, then x equals C is a vertical asymptote. I'm just gonna say VA because I'm running out of space. Not just from the left-hand side, guys. Here's the fourth bullet. I'll write the fourth bullet here. If limit as x approaches C from the right-hand side. Remember, C is a number, a specific number of some function equals positive infinity or negative infinity. It could be either or. Then x equals C is a vertical asymptote. Is it possible to approach C from one direction, be a vertical asymptote, and from the other not be a vertical asymptote? Yes, it is. What if you have a piecewise function? So what if you have something like this? I'm going to call that C. And from the right-hand side, it looks like this. And from the left-hand side, it looks like, let's go this way. See? So yes, from the left-hand side, there is no vertical asymptote. From the left-hand side, you just hit whatever that y value is. But from the right-hand side, yeah, it's a vertical asymptote. So even though it's not a vertical asymptote from the left-hand side, x equals C is still a vertical asymptote because you don't cross it from the right-hand side. Did that make sense to everyone, guys?
Just to clarify, but if we were to say limit as x approaches C, it wouldn't exist, right?
Yeah, you can say does not exist. Well, okay, on this one you can say does not exist because from the right-hand side it's positive infinity, from the left-hand side it's some number. But, big but, sorry guys. If you say limit as x approaches C from the left-hand side, this one does have a limit. It's whatever this number is, whatever that number is, from the left-hand side. Did I answer your question there, Mazuka? Guys, did all that make sense or no?
Yeah, but if you said the limit as x approaches C, that would not exist because they don't match, right?
Correct.
Okay.
They don't match. One from the left-hand side is a number, the one from the right-hand side is positive infinity, so they don't match. Then you go back to your properties. All right, here we go. Theorem properties. I didn't label theorem 1, guys. Obviously, I stole this from some textbook. Anything that is colored is probably coming from a textbook. I don't remember what textbook this is. Maybe Demano Waits, maybe Larson. They don't do a really good job of putting the properties here. They kind of do, like they do a good job, but they kind of cheat you guys a little bit. So I'm going to write them here, what you can write in math. If you never want to write these properties down, that is fine. You can just write your numbers or whatever. So it says let L, M, C, and K are real numbers. So they're just numbers. And limit as x approaches C is f of x, which equals L. So I can go back and forth between these two expressions. And limit as x approaches C of g of x equals M. So I can go back and forth between those expressions. So then it says limit as x approaches C, C is a number, of these two functions, f and g. And they just tell you equals L equals M. And that's fine. I would have liked it if they would have said something like this. Limit as x approaches C of f of x plus limit as x approaches C of g of x. Because that's the same thing. And I guess I could put an equal sign there like that. So there it is, guys. All I did was whatever the limit as x approaches C of f of x is, whatever that is, you add it to the limit as x approaches C of g of x. And maybe you're saying, Chavez, you're just making life harder. No, I'm just trying to show you guys different math symbols that they might, so you don't freak out whenever you see it. Same thing for this one, guys. They're just subtracting them. So if you want, just change that plus to a minus. Limit as x approaches C of f of x minus limit as x approaches C of g of x. So same thing again. F of x times g of x, they're telling you L times M. Well, look, L is this and M is this expression. So properties, limit as x approaches C of f of x, whatever that is, times limit as x approaches C of g of x. So there's all these different ways you can write it. Travis, I don't ever want to write, all right, fine, don't write it. Just write the number, whatever the number is times whatever the other number is. This one, I do like to put the k in front of that limit, guys. That k is just a constant, so you can see k times L. So this I do like to do from time to time. K limit as x approaches c of f of x. So you can see that. It's k times whatever that is. I do like to show that one because that one does come out often. Again, same thing here, guys. What is L? L is limit as x approaches c of f of x. And all you're doing is dividing by limit as x approaches c of g of x. As long as the limit for g of x is not 0. And I'm not going to bother with number 6. That's just power rule, guys. So that just means if you have like limit as x approaches c of f of x raised to the third power square root of that. That just means you can just do f of x to the 3/2. That's all it means. See, simple, guys. Simple. All right, let's continue, guys. So here we go. There's here, I'm just going to use my properties. It really is that simple. If you don't want to write those down, that's fine. You don't have to, especially when they're this simple. So this says limit as x approaches 4 of g of x plus 3. You can rewrite this as limit as x approaches 4 of g of x plus limit as x approaches 4 of 3. See? And it becomes simple. Well, I already know what this is. That is just, oh, I should have changed that number up. 3 plus, well, limit of a constant is just whatever that number is. So that's going to be 3. In case you're confused, that's like saying this, guys. That's like saying my function y is always 3 no matter what. So it doesn't matter what I approach, it's always going to be 3 for this part. So now that limit is just 6. Chavez, you're making this harder. I could have just done 3 plus 3. You're right. Just do 3 plus 3. You're right. You're 100% right. Letter B, limit as x approaches 4 of x times f of x. You can rewrite this as limit as x approaches 4 of x times limit as x approaches 4 of f of x. And if you're confused, you can put giant parentheses so you can see what's what. So what's the limit as x approaches 4 of x? Just 4. So 4 times, and then the limit as x approaches 4 of f of x, that one is 0. Oh man, I should have made a different number than 0 because that's not fun. So it's just 0. Chavez, I could have just done 4 times 0. You're right. Just do 4 times 0. All right, I'm going to take your advice. Your advice. It's actually me just talking to myself, right? But I'm going to take your advice. I'm going to listen to you guys. This says g squared of f of x. Oh, I'm just going to take that number 3, and I'm going to square it. There it is. You guys are happy now. Your advice. It says g of x times f of x minus 1. X is approaching 4. Both of them have x approaches 4. So I can just go 3 over 0 minus 1. So I get negative 3. There it is. We're done. Yay. Oh, that happy face came out weird. Never mind. All right. All right, guys. And now we're going to do fun stuff. The rest should be pretty simple here. I think you're going to like it. Don't worry. We're almost done. Let's see. Yeah, we're almost done, guys. Okay. Example 2. We have limit as x approaches c of f of x is 3. Okay, so they're all approaching the same value, 3, 5, and 2. And oh, I think I took these from UH. They look like they're from UH. So again, g of x is cubed. So I can just write whatever g of x is. That's a 5. So I'm going to say limit as x approaches c of g of x. I guess I didn't have to write it. I could just put the answer immediately. 5 cubed. 5 times 5 is 25. 25 times 5, if I have 5 quarters, that's $1.25. So 125. All right, here we go with this one. This is actually a derivative, but we don't know that word yet, so we're not, maybe I should not have said that. Okay, I'm sorry, guys. Pretend I didn't say that word. So it wants us to do this. Let's figure out what f of 9 is first. So f of 9 is 9 squared minus 9 times 9. 81 minus 81, that's 0. All right, so limit as x approaches 9 of f of x, which is x squared minus 9x minus 0. So there's no reason to put the minus 0 there, over x minus 9. If I do direct substitution, at the moment, you get 0 because look, 9 squared, 9 times 9, you get 0 over 0. But You can either do a table. We're not going to do tables. You guys are already tired of tables. I'm going to factor out an x, guys. Limit as x approaches 9, factor out an x, and then I'm going to write x minus 9. You still have to write the word limit because we have not evaluated it yet. So make sure that's the number one mistake, that you guys don't write the word limit there. X minus 9. And now I can cancel out. I put parentheses in the denominator. You didn't have to. Now you can cancel out the x minus 9. Now I'm ready to evaluate it. And now you can give the answer. So this limit is just 9. In case you want to know how this graph looks, it looks like y equals x. So it looks like this. But when you get to 9, you have a hole. So 9, then a hole. It looks like that. And that hole is located at 9. Because it's just y equals x. See, isn't math beautiful, guys? Okay, here we go. We're gonna see if we really learned about horizontal asymptote. Oh man, I gave it away, darn it. All right, limit as x approaches infinity. As soon as you see this, start thinking horizontal asymptote. Now, do you remember from Algebra 2, we also did it in pre-cal, but it was an Algebra 2 lesson. Do you remember your rules for horizontal asymptote if it's a rational function? So I'm going to put side note for you guys. Side note, it only applies for rational functions. If the degree of the numerator, I'm going to put numerator, denominator. If the degree, we're talking about degrees, guys. If the degree of the numerator is larger than the degree of the denominator, you have no horizontal asymptote. If the degree of the denominator is bigger than the degree of the numerator, your horizontal asymptote is y equals 0. If the degree of the denominator equals the degree of the numerator, you look at the coefficients in front. Coefficient of numerator divided by, sorry that my coefficient of denominator. Sorry guys that my handwriting sucks there. I'll put another example. I'm gonna make one up in a little bit. All right, so here we go. Example 4. The highest degree is 1. The highest degree is 2. The degree of the denominator is bigger than the degree of the numerator. So because the degree of the denominator is bigger than the degree of the numerator, this one is approaching what?
0.
Yeah, 0. Now let's not be robots. It is so easy to just memorize these rules. So easy. But let's not be robots. Why is that? Think about it. The denominator is growing faster than the top, guys. The denominator is growing faster than the top. So Chavez, what are you trying to tell me? I don't know these things, that the denominator is growing faster than the top. What I'm trying to say is, look, 1 divided by 1 is 1. And don't worry, I know that I'm going to keep the numerator constant, but it's the same concept. So I'm going to keep the numerator constant. 1 divided by 10 is 0.1. 1 divided by 100 is 0.01. 1 divided by 1,000 is 0.001. Look what happens. As the denominator gets bigger, the output is getting closer and closer to 0. So let's not be robots. Let's make sure that we understand. Example 5. The degree of the numerator is bigger than the degree of the denominator. You don't have to do anything. It's a polynomial. We already know it's one of these. No horizontal asymptote. If you want to put infinity, you can. I'm going to put does not exist. Both answers are correct. Let me add another one. Let's call it example 6. Example 6. Y, I'm going to say limit as x approaches, and oh, you know what? Let's do a fancy one. I just thought of one. Negative infinity of square root x squared plus 5x plus 10 over 3x. Ooh, all right, guys. I like this problem that I just made up. Go ahead and text me your answer through private DM. And it's okay if you're wrong. It's okay to be wrong. Take 1 minute. Oh, I'm loving this question, guys. Man, so close, guys. You guys are good, but all right, let's go ahead and start talking about this. All right. Before I continue, am I approaching positive infinity or negative infinity?
Negative.
Negative infinity. All right. We already know that we're going to be looking for horizontal asymptote. You're right. A lot of you are getting the right number, just not the right sign. You are correct. Who cares about the 5x plus t? You just care about the end behavior. The square root of x squared, you're right, is x. And the bottom is 3x. So a lot of you are getting the correct number, 1/3. But you fail to realize in the top, in the numerator, look, this is being squared. So I'm approaching negative infinity. So anytime I have a negative number and I square it, will that negative number still be negative?
No.
No, it will not. I'm squaring it, guys. Look, this is what you're doing first. You got to square it first and then take the square root. So the top part, the numerator, is always positive. Numerator, always positive. Always, always, always. But the denominator, I'm approaching a negative number. So the denominator is always negative. Denom, it sounds like a name. Denom is always negative. Well, it actually does sound like, it sounds like someone's name is Denom and she's always negative. But that's by coincidence. The denominator is always negative, guys. Chavez, why is it always negative? Well, because I'm just talking about 3 times x. If my x values are always negative, 3 times a negative number is always going to be a negative number. So my numerator is always positive. Why is it always positive? Because I'm squaring it first and then square rooting. So I have a positive numerator divided by a negative denominator. So what's going to happen? Negative 1/3. This has a horizontal asymptote of negative 1/3. Did that make sense to you guys?
If you were to do it as x approaches infinity, would it be positive 1/3?
Yes. Yes. If I were to do this as x approaches infinity, it would have been a positive 1/3. And relax. I know what you're saying. You're like saying, man, Chavez, that was hard. It is hard initially, but once we start doing more and more, they get easier. As long as you understand the background. If you're a robot, it's going to be hard forever because you don't learn. Because you're just doing like, oh, I'm a robot. I'm just using these rules here. But if you understand the concept, you will never, like you will always get it right. Things will get easier for you because you understand it conceptually and you understand it deeply. So make sure you try really hard to understand what's really going on, guys.